Hello and welcome to my presentation about propelling Space Team Aachen, Space Team Aachen's picosatellite AQUIS. AQUIS stands for Aachen's Qube in Space. My name is Alex. I'm studying aeronautical engineering and astronautics at the RWTH University in Aachen, Germany. And besides that, I'm working as a propulsion team lead at the Space Team Aachen for our satellite project. Right, so who are we? As Space Team Aachen, we are another student association, this time from Germany. We're doing rocketry, satellites, rovers, also scientific experiments. Besides that, we do events, marketing, sponsoring. And STEM outreach, and at the moment we are over 170 active members, so we are quite a big student association, but we also have lots of projects that I will show you on the next slide. What are our goals? Mainly to share a passion for space engineering and space exploration. Also compete in international competitions with our rockets and our rovers, and to get hands-on experience for students, get some practical experience and work on real space projects, and promote future aerospace projects in Aachen and at our university, and most important, make friends for life, and that's also why we're here. Exactly. So what are our projects? At the moment we got 7 projects, four rocket projects. We got Alia, which is our thrust vector controlled rocket. We got Aquila Maris, which is the follow-on project of our competition rocket Aquila, and it will be used as a demonstrator rocket for the German Offshore Spaceport Alliance. So this is a rocket that will be launched next year from a ship in the North Sea, which I think is pretty cool. Then we got a Star rocket. It's a hybrid rocket funded by the German Space Agency. And we got a new project called Hopper, which is basically kind of a vertical takeoff and landing vehicle. Inspiration obviously from SpaceX. Then we got a cooling experiment called TRACE. It's the first student-developed transpirational cooling system. It's part of the program from the German Space Agency together with the Swedish guys in the Rexus program. We got a rover project meant to participate in the European Rover Challenge 2025. And that's why we're here today. We got AQUIS, our PocketQube project that I will present to you now. So AQUIS is our picosatellite program. We basically have the same approach like other guys. So we want to build an iterative series of many PocketQubes. This is AQUIS 1. The highlights of AQUIS 1 are an active ADCS system, which will allow us to stabilize the satellite. We got a ground station thanks to the University of Applied Science in Aachen to communicate with our satellite. Our payload is first of all a camera for Earth observation mainly, and we are using a 3D printed structure made of PBF-LB, which stands for powder bed fusion with a laser beam. And you can see the structure right here. And of course, it's the 3D printed one, but so we have to do heat treatment processes, also surface treatment processes after manufacturing it. Our electric power system consisting of deployable solar panels and a battery cell. And we are trying to build a self-developed onboard computer for data handling. And that's also where you can see our focus is really on education and learning from this project. So as I said, AQUIS is an iterative series. At the beginning, when we were starting with this picosatellite project, we were thinking, well, we actually want to do everything, and so we even implemented tried to implement a propulsion system in a 1P PocketQube. And for our first satellite, this was quite ambitious, and during the design phase, we realized it's really quite complex and there are a lot of challenges, and that's why we decided, okay, for the first satellite we won't do propulsion, But nevertheless, we're still working on it, and I'm part of the propulsion team, and that's why I today want to focus on the propulsion system, which may be implemented in the next satellites from our team. So as we already heard, space debris mitigation is a big topic, and it's also a regulatory topic, and it's it's a real problem, space debris. I'm pretty sure many of you have seen this this video, which shows the space debris, and that's why we really are focusing on the development of propulsion systems, because we don't want to be part of the problem, we want to be part of the solution. And that's our goal for why we started looking into propulsion systems, even for picosatellites. Right, so here's another cool example for why propulsion is great, because we need to deorbit. This is an example of the ESA's Aeolus mission re-entry. I think this is pretty cool. This was taken by this video was taken by a Fraunhofer Institute, and I may also be slightly biased because I'm also working at another Fraunhofer Institute on the development of the laser for the Aeolus follow-on mission. So I think this is great inspiration for deorbiting and sustainability in space. So propulsion for picosatellites, what are the actual requirements? Well, first of all, it has to be simple, because with the space is there's just not much volume there. We don't have we don't have the mass, so it should also be efficient, and of course it should operate safely. We don't want to be just space junk when we're sending our satellite up there. That's why we started. That's why from the beginning chemical propulsion systems are not suitable for these kind of satellites, and we started to look into electric propulsion systems, and try to figure out which one may be the best for our project. And we came up with a pulse plasma thruster, or kind of, it's a vacuum arc thruster that you've already heard of yesterday from Paul. We called it ARI, which stands for Aachen Research Ion-Thruster. You can see the first design here. And to give you a brief overview, propulsion in a nutshell, what are the tasks? I already said deorbiting is its main goal, but it could also potentially increase the mission duration due to orbit change, and maybe one day we can implement a collision avoidance strategy with this propulsion system. Exactly. After listening to the panel yesterday, Tibor said it's very important to look at the interfaces. And so what are the interfaces for our propulsion systems? Of course, we need power, so the electrical power system is there. We maybe also need interface with the thermal control system, because the thruster might get hot when we fire it. The structure and mechanics, of course, we have to attach our thruster somewhere, and the OBC for thrust control. So when we're looking at the design, I will explain the working principle on the next slide. We are basically using a copper anode and a tungsten cathode. Between those two is a insulator, where conductive graphite paint is applied on. And how does it work? I know Paul explained it yesterday already, but I think it's a great technology, so it doesn't hurt hearing it twice. And by the way, that's also really cool for us coming here and listening to talks like from Paul. It's great inspiration, or from other guys. For example, the complex ADCS system that the University of Luxembourg was building. It's quite impressive, and it's basically all one of our goals here, to learn from you and get some inspiration. And that's really cool. Just a side note. So how does it work? We apply a very high voltage peak, which creates highly energetic cathode spots that you can see right here between the anode and the cathode. These cathode spots induce a high current vacuum arc, and these high energy concentration basically lead to small explosions on the cathode surface. And these explosions propel particles out of the thruster and create thrust. So very simple working principle, and also very easy design. So then we tried building ARI after designing it. Here you can see that we are using a spring to push the cathode right onto the conductive layer to minimize the distance between the anode and the cathode. From how do we create this high voltage peak? We're using an electrical booster circuit that you can see here. So this is just a mock-up for the first prototype. We're using IGBT transistors and an Arduino to control everything with frequencies of up to 8 Hertz. And as you can see here in the picture, the thruster is quite small, so obviously, because we're building it for picosatellites, it's not much bigger than a €2 coin at the moment, and there is also potential to get even smaller. Yeah, so we just conducted our first tests of ARI last week. So yeah, I will show videos of them later. We were lucky to conduct our test at a vacuum chamber at the Institute of Structural Mechanics and Lightweight Design at the RWTH Aachen University, so shout out to them. Then we were building a test stand with an exchangeable target for proof of concept tests and also further research. And the good thing about this vacuum chamber is that it has a really, here you can see this, there's ARI or thruster. And the good thing about the vacuum chamber is that it has a really nice window, so we can see a lot during our tests, and it also reaches vacuums of up to 10 to the power of -6 millibars, which is quite nice for our tests. Yeah. So what does our testing strategy look like? Of course, we have to measure the thrust somehow, and therefore we're using a pendulum method. So basically, we're putting a pendulum right in front of the thruster and measuring the rash of the pendulum target, depending on how much the rash, depending on the distance, we can calculate the overall thrust. Of course, we want to optimize the thruster somehow. So in the future, we will be looking into different materials for our cathode, which is basically our fuel. So at the moment we're using tungsten, but we can also use bismuth or steel or meteorites. The voltage level maybe obviously is very important for the thrust level, and since we aiming on building this one for a satellite, we will have to use DC-DC converters inside the satellite, so it kind of will limit us, but that's why we want to test it. Also different cathode geometries. Here you can see, for example, a cathode with a conic shape. We want to investigate the influences of different geometries. How does the frequency influence the overall lifetime is very important, obviously, and also potential add-ons like, for example, magnetic coils to better streamline the particles that we propel out of our fuel. Right. So here I have a video of ARI in action. I hope it's working. Yeah, sorry for the scale, got messed up. But yeah, you can see here on this side you saw those cathode spots, and remembering the picture from earlier, these are exactly the spots where the particles propel out of the thruster and create thrust. And if you look at the cathode right after the test, you can also see them right there. So you can see that we're really using the material there. Yeah, but we are very happy that we can show you these pictures because we just finished our first test last week. Because we got a lot of challenges during building the thruster. As I said, we are a student team, so basically we're doing everything in our free time. It's actually not related to a university at all, and some of us most of us have to work part-time, so there's not that much time for building it. And there are a lot of challenges, and sometimes it's even we make easy mistakes, and it takes a long time figuring out why stuff is burning up. So, for example, if you look at these two kind of breadboards, they kind of look the same, but they aren't, as you can see here. And then sometimes it takes a long time figuring out why your transistor is burning up all the time, even though it's just an easy mistake. Or another one, if you don't apply the graphite layer between the anode and the cathode very homogeneous, then you get really weird thruster behavior. And yeah, this is also part of the journey, figuring out what went wrong and how to learn from these mistakes. Or as Thomas Edison once said, I have not failed, I've just found 1,000 ways that won't work. And yeah, this is also great for us to learn from you and get some inspiration, talk about our thruster, developing it, and yeah, feel free to ask any questions, and thanks for having us.
Any questions for Alexander? I'll go to Paul first.
Thanks, Alec. Great talk. Wondering, what's the peak arc current you guys are running it at?
Peak arc current, I can tell you the peak voltage, but not the peak current, because the oscilloscope that we used last week, yeah, was quite bad. So yeah, we will text after the next test.